Hello, this is Concrete Path, and this lecture will be talking about that stress concept. That stress concept, we were right. Stress concept. This is the first method to calculate the stresses in the pre-stress concrete beam. To calculate the stresses in the PSC beams, PSC beams. So this is your stress concept. So it's saying that generally you are applying that moment, you're applying that load, you're applying that pre-stress load at some eccentricity from the neutral axis. So that's your E. And because when you transfer those two effects, I would say one of the direct stresses that gets developed, that is equals to P by A, and that is constant for all those fibers. All those fibers having same stress of P by A. And because of that moment that has developed, that is a hogging bending moment. That's hogging bending moment equals to PE. And because of that, we have negative at the top and positive at the bottom. That is tensile at the top and bottom compressive. Then we write that PE. This is your moment, and when you write that section modulus, moment by Z, that is your bending stress. So PE by Z, and at the top we have we are going to write PE by Z also. And if you apply the moments also, let's say you applied some positive bending moment because of those external loads, sagging bending moment has developed because of those external loads. I would write it as MA. That is because that would say that MA means that moment because of the dead load and because of the live load. That's what I am writing as MA. That means M all. That is because of M live plus M dead, M live plus M dead, and because of that sagging bending moment, your top fibers would be having compressive stresses and bottom fibers would be having tensile stresses. So I would write positive M A by Z, and here we have negative M A by Z. So then I would say, what are the stresses at the top? Stresses at the top is positive P by A, negative PE by Z, and positive MA by Z. And stresses at the bottom fibers, we are calculating for the extreme fibers in the concrete. Once our stresses at the concrete extreme fibers are lesser than the permissible values, that means all other points, all other fibers are safe. All other fibers are also safe. So I would say stresses at the bottom is P by A plus PE by Z and minus MA by Z. And if I talk about concentric tendon, if I talk about, if this was your eccentric tendon, that means it's having some eccentricity. The tendon is having some eccentricity. Tendon is having eccentricity. It's having some eccentricity. Now, second case is that if there's no eccentricity, if there was no eccentricity, that means the tendon is concentric. Tendon is concentric. That means along the neutral axis line, along the neutral axis of that beam, let's say this is your beam, and this is our neutral axis along the length, and along the section neutral axis is in this way. I would say your what you call as your tendon has been placed in the same along the same line. This is your tendon, and you're applying that P force along that same line. That means E is 0. That is E is 0. So if I have that section now, I'm representing this plane section in terms of a line. So if I have the section on that section, there is application of that Prestress force P, okay, and that I am showing it as a P acting along the line of neutral axis. That means E is equals to 0. So your direct compressive force would be equals to P by A, and because of the eccentricity, I would say eccentricity is 0, so that part is equals to 0. That part is equals to 0. Now if I talk about the external moments, because there was some dead load, there was some live load, and it has provided you sagging bending moment of WL square by 8. That's positive, positive, positive. So top compressive, bottom tensile, top compressive, bottom tensile, top compressive, bottom tensile. So top M all by Z and bottom M all by Z for the symmetric section. We are calculating in terms of section modulus. Your section modulus on the top side is also same as that of section modulus on the bottom side. Okay, let's take that what you call as, so I would say that your external bending moments, you can see here, because of some external bending moments that was developed because of those external moments, you had some tensile stresses. These are your tensile stresses. So this would ensure that cracking of the concrete can appear. That concrete is going to crack because of these. Concrete is going to crack because of these stresses. And to avoid these cracking of the concrete, your what you call as P into E has came into effect. Your PE has came into effect, and because of this compressive stress also, it's trying to have a negative effect here. If there is some positive value here, and we have some negative value here also, so net value might be lesser than as compared to the initial case here. So your effect of that cracking gets decreased. So cracking possibility reduces because of this pre-stress concrete. Do you see that cracking stress gets developed, cracking tendency gets developed, gets reduced, sorry, I would say. Let's take that problem one for your stress concept. Problem number one for your stress concept. Let's go for that. Number one, we have that UDL. That's saying we have all of those UDL. W all is 16 kilonewton meter. That's because of the dead load and because of the live load on this beam of length 6 meters. Simply supported beam, 6 meter length. L equals to 6 meters. And the tendon is placed such that if you have this cross section, it's placed at some eccentricity. That's if the total is 600, depth is 600. Okay, if the total depth is 600, the eccentricity is 100 millimeters. So P force is somewhere here at some eccentricity of E equals to 100 millimeters. This is your E, 100 millimeters. And I would say, and the problem is saying get the extreme fiber stresses at the mid span section. So we need to get the F top, F bottom. These are the extreme fibers. These are the extreme fiber stresses. Because of this, because of the combined effect of P, P, E, M all. Let's go for that. Can calculate the moment developed at the bending moment developed at the midspan because of the external loads. Is that 16 L square by 8? That is equal to 72 kilonewton meter. WL square by 8, 72 kilonewton meter. Let's have that now. I would say because of this P, there is some hogging bending moment developed, and there's some compressive force of P by A developed here for all those fibers, and there's some hogging bending moment. Because of that, you have compressive bottom and tensile top, and at the top we have some section modulus PE by Z, Z top, and PE by Z bottom. But your Z top and Z bottom, they are same. See, if you have the section, symmetric section, where your Y bottom is equals to D by 2 and Y top is also D by 2. So that means Z top and Z bottom is equals to same, that is BD square by 6 for the symmetric section, rectangular section. And third one is that effect of the moments, effect of those external moments that was sagging, and because of that, top compressive, bottom tensile, M all by Z, M all by Z. And let's get those values now. Let's solve those values. Your P by A value is equals to your P by A. We can write what is the force. What's the force P we are applying on the section? It's saying that we are applying that pre-stress force of 960 kilonewton. 960 kilonewton. So let's go for that now. You would say, what's the value of P by A? I would say P by A is 600 kilonewton divided by A. Area of the cross section of the concrete is 0.4 into 0.6 meters square. And after that, we have one more value of PE by Z. 600 kilonewton. Eccentricity of E, that was 100 millimeters, 0.1 meter, and divided by Z, BD square by 6. B D square into 6 divided by 6. So that's your BD square by 6, that's meter cube. And third value is that MA by Z. We need to calculate value of MA by Z. That's moment developed was equals to 72 kilonewton meter. 72 kilonewton meter. 72 kilonewton meter divided by Z, section modulus. Okay, BD square by 6. So you solve these three values. They are equals to, this one is a value of 4 megapascal. This one comes out to be equals to 4 megapascal, and this value is equals to 3 megapascal. And if I want to calculate now what is the equation for stresses at the top, I would say stresses at the top is equals to P by A minus PE by Z and plus M by Z. And stresses at the bottom, if I want to say what are the stresses at the bottom, that is P by A plus PE by Z minus M by Z. So I would solve that 4, 4, 3, 4, 4, 3. So I would say 4 minus 4 plus 3 and 4 plus 4 minus 3. So at the top you had stress of 3 megapascals, and at the bottom fiber you have stress of 5 megapascals. So this is our variation. This is the stress variation at the midspan. Stress variation at the midspan, positive. There would be some C-force also at some location, and that's not our topic here. This is our stress concept. So this is your variation of the stresses for this problem. Okay. Let's take one more problem. It's saying that we have a cross section of the beam. Prestress beam is there. It's having some dimensions of 300 cross 600, and the eccentricity E equals to 80 millimeters below the neutral axis. That means P force is acting somewhere here on this cross section. This is P force at some eccentricity of E from the neutral axis. This is neutral axis, and we have 5 bars. The prestress is developed because of the steel bars, and steel bars we have number of bars, 5 bars of 12 phi, and their stress was equals to the initial stress in the steel bars. Initial stress in the steel bars was equals to P naught equals to 800 megapascals. So how can you apply this stress in the bar? Actually, how can you apply this P naught stress in the bar? That means this stress is corresponding to some deformations, elongations in the bar. When you apply that pull on the tensile bar, when you apply that tensile force in the bar, there will be some deformations, and because of the deformation there is the strain, and because of the strain there is stress. So that 800 megapascals is corresponding to some strain value of let's say value of E is 2 into 10 to the power 5 megapascal, and there would be some strain at that value. So at that particular value of strain, delta by L, that means you have provided some elongation for particular length of the beam, particular length of that steel bar, so such that your stresses in the steel wire was 800 megapascal. So problem is that you have 5 bars which would be having some area of the steel bars, and I can get the P force. The P force would be equals to area of the steel bars into stress in the steel bars. So let's calculate that P force. That P force would be equals to 5 bars of pi by 4 revolve square millimeter square into 800 megapascals, and that P force is equals to 452.389 kilonewton. 452.382 kilonewton, and same force is transferred to the concrete because of the bond action we have. Because of the bond action for pre-tension beam, but we don't know by which method we have transferred this force. For the post-tension, because of the anchoring of that those bars, that force was transferred simultaneously. But we don't care about what was the method of that transfer of the force. For this case, we are solving only the stresses. Finally, I would say that P force is applied on the concrete section, and because of that, your stresses would be one is your P by A, and next one is that PE by Z. Bottom tensile, bottom positive, top tensile because of hogging bending moment. Because the eccentricity is below the neutral axis, PE by Z. And is there any moment? Yeah, it's saying that if there is a beam, of length L, how much moment should we apply because of those because of those loads W live plus W dead, because of these loads, these loads, how much moment we should apply, how much moment should we apply such that so the problem is that how much moment we have to apply such that tension at soffit equals to 0. Tension at soffit equals to 0. Soffit of beam equals to 0. That means it's talking about this soffit, the base of the beam, the bottom of the beam, that's we call it soffit. So we want that stresses at the bottom of the beam equals to 0, such that the final value is equals to 0. Why 0? Because I don't want tension in the beam. I want a critical location. I want a critical value that my stress variation should be in this way, that this is top should be having some compressive stresses, but the bottom should not go under tensile stress. So I don't want tensile stresses in the concrete in the bottom side. This is the condition. The condition is saying that I don't want any stress that is tensile in the bottom. It's saying I want tension to be 0. That means I want a stress condition such that the stress here is 0, such that the stress is at the bottom is 0. So based on these two results, because of this P by A and P by Z, we might be having some stresses at the bottom. But the value of those are both positive. That is compressive. And if I say what is the net value of because of these two, I would say net value of because of these two would be some sort of in this way. But now I have to use this beam now. Actually, I have to use the prestress beam somewhere where the loading would be actual loading would be there. And because of those actual loads, your bending moment gets developed WL square by 8 positive at the midspan, such that it would cause some negative or tensile stresses at the bottom. And finally because of those stresses M applied by Z, it would cause some stresses at the bottom. And finally, I would say the net value of this one and this ones give me some value at the top and 0 stresses at the bottom. I want this condition, final condition, that stresses at the bottom should be equals to 0. That's the problem is all about. That final stresses at the bottom equals to 0. Let's go for that. I would say that your P by A equals to 452.389 kilonewton divided by area of the cross section, 0.3 into 0.6, and your PE by Z is 452.389 kilonewton into eccentricity of 0.080 meters divided by section modulus of BD square by 6. And there is one more, what you call as, there should be some moment applied and divided by BD square by 6 such that overall value is equals to 0. That means I would say stresses at the bottom should be equals to 0 final value. What are the stress values at the bottom? Can you tell me? Because of these three combinations, I would say P by A is positive. This is positive. PE by Z is also positive, and MA is negative. MA by Z is negative. So finally, I had to equate it with the 0. Our tensile stresses we keep them negative, and finally I should apply such amount of moment which would cause net value of stress at the bottom to be 0. That means it should not be tensile. We can have compressive, but it's talking about maximum. What should be the maximum amount of moment we can apply such that we don't want any tension at the bottom. That means it's saying about the critical condition. Let's talk about that. That means we can solve that moment. Once you solve this part, and you multiply this part there, and you would get a moment applied. What's the moment we can apply on the beam? That is equals to 81.36 kilonewton meter. I hope you got the problem. You enjoyed that. I hope you got that. Okay. Let's take one more problem related to your stress concept. Let's take one more problem. It's saying that we have a beam cross section. We have a beam cross section of dimensions 250 and depth is 375, and the tendon is concentric tendon. That means the eccentricity is 0. tendon is concentric. That means the steel bar is concentric, which implies eccentricity is 0. So if there is neutral axis, that means the P force is acting at the neutral axis location, P force. And it's saying that how much P should we apply. So we have two different cases, we have two different parts of the problem. First part of the problem is that how much P should be applied such that tension is just avoided at the soffit up midsection. Tension is just avoided at the soffit up midsection. Soffit means at the bottom of the beam. Soffit or at of midsection, yeah, of the midsection. But we should know where is the midsection. Let's have the beam. Let's take the beam. I would say there is some beam. I'm applying a live load of imposed live load of 4.25 kilonewton per meter. Okay, and the length of the beam is 8 meter. And I would say there would be some dead load also. That is 25 kilonewton per meter cube into area of the cross section of the concrete. That is 375 into 250. 0.375 into 0.250. So this is your dead load of the beam. So dead load of the beam is equals to some value such that finally I would say W all equals to sum of these two is equals to 6.50 kilonewton per meter. And because of this, can you tell me what is the moment that gets developed at the midspan? Because we are talking about the midspan. So moment at the midspan is equals to WL square by 8. And that equals to 6.5 into 8 square by 8. And that value is equals to 52 kilonewton meter. 52 kilonewton meter. Now, this is your positive bending moment. And it's saying that how much P we are applying concentrically such that eccentricity is 0. And I want tension at the bottom to be 0. Let's take that case. You have this section, you are applying P. That means E is 0. If E is 0, so let's have those stresses. That means the stresses would be equals to P by A, compressive, and because of the moments, because of the external moment MA, your stresses at the bottom is MA by Z. Let's say that the condition is saying I want F at the bottom, that's at the soffit, that should be equals to 0. And that's because of P by A, and that's because of minus MA by Z. So let's solve the values of P. I don't know the value of P. That's the problem is saying get the value of P. I would say P by BD minus, I would say that equals to moment, because of that moment comes out to be equals to, what was the moment value we have? Moment was 352 kilonewton meter. Let's solve that. 52 kilonewton meter divided by B divided by the section modulus Z, BD square by 6. So that P value is equals to 52 kilonewton meter into 6 divided by Z divided by value of D, that was 0.375 meters. So you would get a value of P equals to 832 kilonewton. Do you got this problem? I think it was easy. Now second case of the problem is that, second part of the problem is that you need to say what should be the amount of P that has to be applied. If eccentricity is there, if the tendon is eccentric. Now tendon is not concentric. Second case is that tendon is eccentric. That means eccentricity for the second case is 65 millimeters. So I want that bottom stresses at the bottom to be 0. What is the critical condition? What is the maximum load we can apply? What is the P we can apply such that stresses at the bottom is equals to 0? So for that, I would say your diagrams would be having some extra part also. Let's say there's some neutral axis somewhere here. Let's remove this. Let's have the diagram again. I would say this is our neutral axis and there's some eccentricity P. I would say the one of the stress would be P by A, second stress would be minus plus PE by Z, and third stress would be plus minus M by Z. We already calculated these two. Now we need the value of P. Let's solve that. I want stresses at the bottom to be 0. I want stresses at the bottom to be 0. So I would say stresses, for the stresses at the bottom to be 0, I would write P by BD, because area of the cross section of concrete, that is BD. So P by BD positive plus PE by Z. Z is BD square by 6, and that should be equals to, yeah, let's write in this way. That's minus M by Z. So that should be equals to 0. Then I would solve it. I would write P. Your BD goes in every term, BD goes. So you are left with P 1 plus 6E by D equals to M 6 by, this was your D, M 6 by D. So your equation becomes, finally I would say P becomes equals to 6M. Your value of M was 52 kilonewton meters divided by, this was your D value. Your D value was 0.375 meters, and you have to divide this entire part 1 plus 6 times eccentricity. Eccentricity was given to you as 65 millimeters, 0.065 meters, and divided by that value of D. The value of D was 0.375 meters. So you can get the value of P, that is equals to 407.843 kilonewton. Okay, this is the force that you need to apply, 407. Now if you compare it with the previous problem, you had initial value of P was 832, I think. This was your 832. Initially in the previous problem, in the case 1, your P was applied as 832. But in this case, your P was applied only how much? 407. So that's almost 50% less. That's almost 50% less. So your force P2, that's less, almost 50% as compared to initial case. That means by providing some eccentricity below the neutral axis, your moments, your tensile stresses can be counteracted very effectively. So you just provide some eccentricity of that load below the neutral axis such that it would cause hogging bending moment, and your tensile stresses because of the external bending moments can be counteracted. This was a very beautiful problem. This was a very beautiful problem. Yeah, okay. Let's go for next problem, that's unsymmetrical eye section. Unsymmetrical eye section. Okay. 100, 300. So this is your unsymmetrical eye section. Unsymmetrical eye section. Okay. This cross section of the beam, Prestress beam. Now you need to say what is the stresses at the center of the beam. Stresses at the center of the beam, that's at the top and bottom fiber, those extreme fibers of that mid span section, bottom fiber. Okay. So beam is that you have 8-meter span beam, effective span 8 meter, and subjected to load of live load, that's live load of 2 kilonewton per meter. So first case is that you need to say what is the, you need to say because of P load and because of the self weight, get the stresses. So first part of the problem is that because of the, get the stresses because of the P load, its eccentricity, and because of the self weight. And second case is that calculate the stresses because of P, its eccentricity, your self weight, and all the live load you have for on the beam. Let's go for the first case. So but why is the P load is acting? Why the P load is acting? I would say that that's acting at some eccentricity from the bottom. Let's say that that value is 50 millimeters from the bottom. So that's from the soffit. I would say from the soffit, your value of your P is acting here, the P is acting here, the value of P is acting here. That means I have to get the eccentricity from the neutral axis. So I would say this is from the E bottom, but I need from the neutral axis the location of the P force from the neutral axis. So I need to calculate the neutral axis for this unsymmetrical I section. So we need to get the neutral axis location of this, what you call as section, and after that I can say what is the value of E. That's eccentricity of that load P, P force from the neutral axis. So we need to calculate that what is the centroid of that section. Can you calculate the centroid of that section? If I calculate it from the top, I would say your x bar would be somewhere 300 into 60 into 30 plus second area is that 80 into, what is this dimension? Can you tell me? If the total is 400, is this 120 minus 400, is it 280? Is this 280 part? Yeah, 80 into 220, 280, and the centroid would be at 140 plus 60 from the top. And third area is that you have 100 into 60, and the centroid would be acting at 280 plus 60, 340, 340 plus 30. Yeah, divide by, you have to divide it all, divide by total area of that section. The total area of that section is equals to area of the total section is equals to 0.0464 meters square. And finally your centroid would be somewhere at a value of 243, yeah, 156.03 millimeters, 156.03 millimeters from the top, 156.03 from the top. So 156.03. So somewhere, I would say somewhere here. That means this part would be equals to 156.03. So the centroid is here. This is neutral axis. 156.03 millimeters. Can you tell me what is the bottom side? What is the value of y bottom? What is this value y bottom? Value of y bottom is equals to 400 minus 156. 400 minus 156.03. This part would be equals to 243.97. 243.97. And can you tell me now what is the eccentricity of that load P? Can you tell me what's the eccentricity of that load P now? I would say the eccentricity of that load P is equals to 243.97 minus distance from the bottom, EB. This EB was given to you as 50 millimeters. This was 50 millimeters, so we can subtract that. And finally, your eccentricity is 193.97 millimeters. So this is our final eccentricity value. So once I got the eccentricity value, and I need to calculate the stresses because of the P, its eccentricity, and because of the self-weight. So we also need to calculate self-weight, and we also have to calculate the effect of the live load. So first thing is that let's calculate the effect of the moment, that moment developed because of the self-weight. Yeah, let's calculate what should be the dead load of this section. Can you tell what is the dead load because of the section having concrete of unit weight 25 kilonewton per meter cube, and we have the area of the cross section as was given to you as 0.0464 meters square. This is the area of the cross section, so your gamma WD would be equals to 1.1114 kilonewton per meter. And from that, can you tell me what is the maximum bending moment we can have at the midspan because of the dead load? I would call it as MD, that's dead load. That's moment because of dead load. That's 1.114 L square by 8. That is some 9. That is around 8.912 kilonewton meter. And because of the lie load, can you calculate because of the lie load? That's WL square by 8. That is 16 kilonewton meter. So let's have these values, 8.912. Okay. So now first case is that you have to calculate the stresses at the midspan because of the eccentricity of the load P, because of the eccentricity of the load P, and because of the self weight. So I would say the P was acting here. This was the location of P. P was acting here. From the centroid, eccentricity of that load was, what was the eccentricity? Eccentricity was equals to 193.97. Can you tell me what is the stresses we can have? So here we are not going to use that Z. We can have the value of Z as Z top and Z bottom, corresponding to I neutral axis divided by Y top. Similarly, this one is your I neutral axis divided by Y bottom. Okay, let's have the stresses now. Let's have the stresses. I would say this is your, this one would be equals to, this one is your, sorry, this one is your P by A, positive, compressive, and we would be having, because of the hogging bending moment, we will be having negative, positive, and the bottom value. Can you tell me what is the bottom stresses because of the load, because of the moment of PE? What is the stresses at the bottom? Is that PE by Z, what do you call as Z bottom, and is the top value equals to PE by Z top, and that is PE I neutral axis divided by Y, so we would get Y top. We have to write Y top at the top final value. So similarly, this one would be equals to PE divided by I and Y bottom. And third one is that because of the self weight, we would be having sagging bending moment, so bottom tensile positive compressive, bottom tensile and top compressive. Okay, this would be M dead Y by I. This would be Y top, and second bottom one would be Y bottom divided by I. So these values we need to calculate for this problem. So, but the thing is that, do you know the value of I for the unsymmetric section? So we need to calculate the value of I also. Let's calculate the value of I. That is the moment of inertia about the neutral axis. Let's calculate the moment of inertia about the neutral axis. Okay, let's go for that. See, this data was, the neutral axis, I would say Y top was given to you. We calculated that as X bar. Y top was equals to 156.03, and this was your Y bottom was equals to, I would say this is your Y top, this is your Y bottom, that is 243.97. Okay, let's go for the moment of inertia about the neutral axis. So I would say I neutral axis is equals to BD cube by 12. So B D cube by 12 and plus B area of that into D square. The D would be equals to, let's say the centroid of this part would be at 30. Yeah, let's go for the total. Y 156.03 minus 30 whole square. And second area is that 280 into 80, yeah, 280 cube by 12 into 80 into, yeah, plus after that 280 into 80 area into D square, 80 into D square, while your centroid of this part is somewhere here at 140, and centroid of this part from this location is somewhere here. So I would say this centroid is somewhere at 140 plus 60, so I would write 200 minus what, I had to subtract 156.03. Is it true? 200 minus 156.03. Okay, this is also correct. After that, the third area. So because of the third area, we have 100 into 60 cube by 12 and plus area into D square. The D would be equals to, from the top I can, or from the bottom we can take from the bottom. Your total value was 243.97. I can subtract that 30 value here. Centroid is at 30, so 30 square. Is it correct? Yeah. So the overall value is coming out to be equals to 757.45 10 to the power 6 millimeter power 4. So let's use this value for calculation of those stresses. So we'll be calculating those values. We'll be calculating those values. Your value of P, do you know the value of P? Value of P was given to you in the problem as 100 kilonewton. Okay, 100 kilonewton. Area of the cross section is equal to 0.0464 meters square. And I got the I neutral axis as 757.45 into 10 to the power 6 millimeter power 4. And your Z Y top is also given to you, Y bottom is also given to you. Let's go for the calculations. So your first one is that P by A. Let's calculate those individual values separately. If I say F top, what is the value of F top? What is the stresses at the top fiber? I would say that is P by A minus PE Y top by I plus M dead Y top by I. So let's go for those values. Your P value was 100 kilonewton divided by area of the cross section was 0.0464 meters square. And after that you have minus, P 100 kilonewton. Eccentricity was 0.197397. This one 0.19397. And this was your meter. And after that Y top was equals to, the value of Y top is equals to 156.03, and divided by neutral axis I neutral axis, that was 757.45 10 to the power 6 millimeter power 4. So you have to ensure that the units are correct, and accordingly you have to solve those values. And third one is that M dead. Because of the dead load, you had that bending moment, that was MD coming out to be equals to 8.912 kilonewton meter into Y top 156.03 millimeters divided by I neutral axis, that is 757.45 10 to the power 6 millimeter power 4. So finally your stresses would be equals to F at the top is equals to, so after calculations we have came to the value that stresses at the top are coming out to be equals to, so this value is coming out to be equals to minus 0.015 megapascal. And we need to get the stresses at the bottom now. So what is the stresses at the bottom? That is P by A. Okay, that's P by A. And after that we have plus PE by PE plus PE Y top, and here we have Y bottom. So we need to replace that Y top as a function of Y bottom. So we need to replace here Y bottom. So what's the value of Y bottom here? Y bottom was given to you as, Y bottom was 243.97, and rest of the things are okay. Yeah, we need also replace here, in place of Y top we have to replace as Y bottom. So here we have to replace as Y bottom. So this one we have to replace as 243.97 millimeters. So finally your stresses at the bottom would be equals to, stresses at the bottom is equals to 5.53 megapascal. So I can have the stress variation as, I can have the stress variation that at the top I have some stress that was minus 0.015 megapascals, and at the bottom I have a compressive stress of 5.53 megapascals. Positive, negative. This is the stresses developed at the midspan section because of the dead load, because of the P, and because of the PE hogging bending moment. So let's talk about the second case of the problem. It was saying calculate now stresses because of the load, because of P, because of E, because of self weight, because of live load. Because of the live load you have bending moment of 16 kilonewton meter. So we had to add that part also here. Let's add that part also here for the second part of the problem. Let's add also that second part of the problem, that this would be your stresses because of the M live, and here we have Y top by I. At the bottom we will be having M live, Y bottom by I neutral axis. So we can add those values for the top and bottom values. So initially our value at the top was minus 0.015 megapascals. Now we had to add some value of live load, that is 16 kilonewton meter, and the value of y top was 156.6303 millimeters. Then divided by I neutral axis. The value of I neutral axis we know 757.45 757.45 10 to the power 6 millimeter power 4, and accordingly you can get the stresses at the top for the second case of the problem, that is equals to 3.275 megapascal, and stresses at the bottom would be equals to initial stress was 5.53 megapascal, initial value was 5.53 megapascals, and we have some value that's negative value ml, that is negative value, so 16 kilonewton meters into 243.97 divided by 757.45 10 to the power 6 millimeter power 4. This is your millimeter. So stresses at the bottom is equal to 0.38 megapascals. So final stress diagram would be stresses at the top is 3.275 and stresses at the bottom is 0.38 compressive. So this is our stress variation. See, stress variation for the mid-span section subjected to load of P, its eccentricity, M dead and M live. Okay. This was the end of this problem. That was the end of this problem. So one final problem is that we call it as we have this concept what we call as nominal area versus equivalent concrete section. Nominal area versus equivalent concrete area section of concrete section. Okay, nominal area versus equivalent area of concrete section. What that means, that if you have that concrete section of dimensions B cross D, then we are placing some steel bars here, the Prestress bars. So we are placing some steel bars of area AST, and we have some modular ratio of that. Modular ratio is that modulus of elasticity of steel divided by modulus of elasticity of concrete. So that will be having some value almost to say 6, 7, 8, 9, 10. There is some value of modular ratio, and we say that there might be some, we can have some equivalent area also. Till now we were ignoring, we ignored the area contributed by those bars, contributed by bars of the steel, area of the steel. We ignored that area. We say that in usually that in PSC concrete, your area of steel, that's area of the steel, that is usually lesser than area of the concrete section, that's that BD. So we say that this part does not contribute so much in the total area. So if we talk about nominal concrete area, we say that nominal concrete area says that you ignore the concrete, you ignore the steel somewhere here, you just say there is some area, total area BD, and we are going to solve it. For the neutral axis would be at mid-span. So that was your simple case, that neutral axis is at the mid-span, sorry, at the mid-section, mid part of the section. Then what about this equivalent concrete section? It says that I have to replace this, or we can say I have the total area of the section, or area total of the section equals to area of the concrete plus area of the plus m minus 1 area of the steel. So this area of the concrete, we assume that this is almost equals to B times D and plus m minus 1 the area of the steel we have provided, such that it becomes equivalent area of the cross section. And this equivalent area of the cross section is going to resist those what you call as those moments, such that we can have some stresses. So we are going to take that one of the problems such that we are going to solve it by those two different approaches, and we are going to see the variation in the calculations of those stresses. So our cross section is that we have width of 150 millimeters and depth of 300 millimeters, and we have placed four bars of 5 mm diameter. So we have 4 bars of 5 mm diameter. Okay, 4 mm diameter. So eccentricity of those bars, that means the P force is acting at some eccentricity from the neutral axis, that's 100 millimeters. And the stress in the steel that we represent by P naught, initial stress in the steel bars, that was equals to 1200 megapascal. Okay, now we need to get, so we have two different problems. That first one is that you need to get the stresses at the soffit, that means at the bottom, by considering what? Nominal concrete area, by considering nominal area of the concrete section, nominal area. And second is that get the stresses at the bottom, that we also call as soffit, stresses at the soffit by equivalent area of the concrete section, area of the concrete section. Okay, so first case we say that your area of because of these steel bars can be ignored. So if I take that, and the question also mentions that you have to ignore the self weight and live load. Let's ignore self weight and live load. Ignore these effects. You just calculate based on the eccentricity of the load P. Based on the eccentricity of the load P, you just calculate the stresses. I would say you have this section, and your bars are somewhere here such that there is some eccentricity from the neutral axis. Your eccentricity is 100 and P force is there, and so the stresses would be P by A compressive, and there would be some variation of bending stress in this way, that top tensile, bottom compressive, and with the values of PE by I, we can write Z, PE by Z, and at the top also we have PE by Z. Can you get the value of P based from the area of the steel provided and the stress in the steel? I would say P force is equals to 4 bars of pi by 4 5 square into some stress of 1200, and I can get the total force of 94.25 kilonewton. 300 into 150. Okay, so your P by A becomes 94.25 kilonewton divided by area of the cross section is 0.15 into 0.3 meters square. By the first method, that we are going to ignore the area of the steel, and second stress is that this is the stresses at the bottom. We need to calculate stresses at the bottom, that is at the soffit of the beam. So plus, at the bottom we have plus 94.25 kilonewton, and eccentricity was given to you as 100 millimeters, then divided by Z for the section modulus for this concrete section, a rectangular concrete section, that is BD cube by 12, BD cube by 12, yeah, BD square by 6, that's millimeter cube. Then we need to convert those in standard units of Newton per millimeter square, that's megapascal. So the stresses would be equals to 6.283 megapascal by the first method. And if I want to solve it by the second method, that is equivalent area method. Let's take the equivalent area method. So I would say total area of the section now would become A times the area of the the total area would becomes B times D plus M minus 1 into AST. So I had to substitute those values. I would say this is your B into D. B into D was your 0.15 into 0.3 meters square, then plus M. The value of M is given to you modular ratio. That let's take modular ratio as 6. So let's calculate for that. 6 times, I would say 6 minus 1. Area of the steel we know 4 bars of diameter, 5, I would say pi by 4, 5 square. So that value, overall value, is coming out to be equals to, yeah, you can solve that. That's your total area of that and this part is coming out to be equals to m minus 1 ast is coming out to be equals to 392.699 millimeters square, this part of the area. Okay, now I would say that we have to convert it in terms of equivalent area. Let's convert it in terms of equivalent area now. Let's convert it in terms of equivalent area here. I would say this can be transformed into an equivalent area such that at the level of steel bars we can have some area more than the dimensions of BD. So at this location we can increase the area by some amount such that this overall part of this one, such that this part and this part overall is equals to m minus 1 ast. Now because of this your neutral axis would get is going to change. Because of this effect neutral axis is going to change. Now if I calculate from the top, neutral axis dimensions were this was 150, this was 300, and this area is a total area of we have calculated that 392.699 at this location. I know the location, that's it's acting somewhere here at some eccentricity of 100, so I can say this is acting from the top at some eccentricity of 250. So let's calculate the centroid of the total area, x bar. Let's calculate the centroid, that is the neutral axis for this section. I would say 150 into 300, and that acts at 150 plus your second area is that m minus 1 ast, 392.699 acting at this was your 250 millimeters, and divided by total area is 150 into 300 plus 392.699 is equals to 150.865 millimeters. So it's almost equals to 150. Because the area of the steel is less, so I would say the shift of neutral axis is only by some amount of 0.865 millimeters. Because of this small effect of this change, I would say your stresses are not going to change that much, because your area of the steel is very less. Let's try to calculate the neutral axis, that moment of inertia about the neutral axis. I would say let's try to calculate the moment of inertia about the neutral axis. That moment of inertia about the neutral axis equals to 150 into 300 cube divided by 12 plus second one is that 150 into area. So I would say this area into centroid, difference of those. So I would say your centroid is acting here. Total centroid was at 150.865. So 150.865, but your centroid of the BD is acting at 150. So difference of 0.865. Then I would say square, AD square. Then we have third area, that's the area of the m minus 1 ast, 392.699, 392.699, and this was your area, and it's acting at this location, where the it's acting from the top at a location of 250, but your neutral axis is somewhere here at 150.8. So I would say the difference here is 250 minus that location of neutral axis. So I would write here 250 minus the location of neutral axis, 150.865 whole square. That's your second part. So this is your I neutral axis. It comes out to be equals to 341.393 10 to the power 6 millimeter power 4. Once I got this value of I, and I can get the value of y top and y bottom for this section. Y top we have calculated as your value of y top was 150.865. That means y bottom would be equals to 300 minus y top. So let's go for the values of those stresses. I would say that you have this area now I would say that eccentricity is here, at some value of 100? No. Your eccentricity is now going to change. Your eccentricity is now going to change. Can you tell me why? For the calculations of this equivalent area, eccentricity is from neutral axis. We need to calculate from the neutral axis. But your neutral axis is changed by 0.867 millimeters, so your value of E is also going to change. Let's see how. Total was 300. Okay. Initially, neutral axis was at the midspan, but for the second case, for this case, your neutral axis is somewhere here at 150.867. So that means this is your neutral axis, and load is acting somewhere here. So I would say your value of E would be less than, initially it was 100. So I had to subtract that value of 0.867. So this is your eccentricity now. This is your eccentricity of that load P. And because of that, I would say your direct stresses of P by A, and this is your A total here. P by A plus one more stress is there, this one, minus plus, and stresses at the bottom would be P E Y bottom by I neutral axis. So we have calculated those values. I would say value of P was already 94.25 kilonewton, and area of the cross section, total area of the cross section is BD plus M minus 1 AST. And second one is that positive value. We are calculating stresses at the soffit, stresses at the bottom, plus P, your value of P is 94.25 kilonewton. Eccentricity is now 100 minus 0.861 millimeters. And we have one more part, that is Y bottom. Value of Y bottom, that was 300 minus Y top. Value of Y top was your 150.867 Y top. Okay, and divided by neutral axis, moment of inertia about neutral axis, that is 341.39 10 to the power 6 millimeter power 4. So finally you would get stresses coming out to be equals to 6.15 megapascals. So because area has increased, some part of the area has increased, so stresses have decreased a bit. Initially it was 6.283, now the values of stresses are 6.15. And if I say what is the difference, what is the percentage decrease in the stress, I would say that is almost a 2% decrease. So if I increase the steel area, your stress value would decrease by equivalent concrete section. So that was your final problem of that stress concept. Thank you for watching this series. Okay.